biasa pakai. Mungkin di sini, Pak. The honorable speakers, ladies and gentlemen, thank you for coming back to your seats and being ready for the next session. The second session is secret sharing protocols, and we are honored to still have Dr. Romar de la Cruz as our speaker. Please give him applause.
Okay, so for the second part of my talk, my main focus is on the connection between secret sharing schemes and error correcting codes. So we start with the construction of secret sharing schemes using linear codes. So there are two constructions. So the first one I will describe briefly. So this was proposed by Makilis and Sarwate. So the idea is you take, let's C be an NK linear code over FQ, and then take a generator matrix of C. And then let's say the secret is S, element of FQ. So to share the secret, the dealer uses K-1 elements of FQ, and then to form this information vector. So the first coordinate is the secret. And then using this information vector, we compute the corresponding code word. So we multiply the information vector by the generator matrix, so you get code word of C. Now the share of P sub I is the ith coordinate of the code word. So that's the first construction. So to describe the access structure, so the sets that are authorized to recover the secret, we have the following theorem. So let us denote the ith column of the generator matrix by G sub I. So we can characterize the access structure as follows. So if we have a set of shares, C sub I sub 1 up to C sub I sub m, so they can determine the secret. So if and only if they satisfy this condition. This vector is a linear combination of the corresponding columns of the generator matrix. Perhaps this will remind you of the monotone span program construction. has the same property. So to illustrate, I give an example. So recall again the Shamir threshold scheme. So you can construct it using the Reed-Solomon code. So the Reed-Solomon code, it's given by this. So the code words, the coordinates are evaluations of a polynomial of degree less than k. So f of x is a polynomial over fq. So those are the code words of a Reed-Solomon code. And then if you take this generator matrix of the Reed-Solomon code, and then you apply the construction, what you obtain is the Shamir threshold scheme. So that's the first time where the linear codes were connected to a secret sharing scheme. So McEllis and Sarwate showed that the Shamir scheme is a scheme using Reed-Solomon code. So the shares of the Shamir threshold scheme, you can look at them as code word of a Reed-Solomon code. Now, the second construction, so this one, I will focus on this one. It's given by Massey. So it's a little bit different, but it's still a simple construction. So this time we take an n+1k linear code over FU. So the length is n+1. And then we take again a generator matrix. So let G sub I be the ith column, and let S be the secret. So to share the secret, the dealer randomly selects a vector U. U is the information vector with this property. So the inner product of U with the first column of G is equal to the secret. So that's the property. And then using that information vector, we compute again the corresponding code word. So this is the corresponding code word. Now, if you look at the code word, the first coordinate is the secret. That's the secret. And then the other coordinates, they will be the shares of the participants. So the share of P sub I is C sub I from 1 to n. So if you compare with the first construction, in the first construction, all the coordinates are the shares. But for this one, you reserve the first coordinate for the secret. And then the other coordinates are for the shares. So to characterize the access structure, we have this theorem. Suppose we have a set of shares. So C sub I sub 1 up to C sub I sub R. Then they can determine the secret if they satisfy this property. So the first column is a linear combination of these columns of the generator matrix. So these columns correspond to the shares. So this is the one way to characterize the access structure. The proof is straightforward, so I will show one direction of the proof. So suppose we assume the following. We assume that G sub 0 is a linear combination of these columns. So we have the following. There exist constants A sub 1 up to A sub R such that G sub 0 is a linear combination of these columns. Now to determine the secret, you simply perform this operation. So the secret is the inner product of U and G sub 0. And G sub 0 is equal to this linear combination, so you will obtain this. And at the end, what you get is a linear combination of the shares of the participants. So their shares, they can recover the secret. So similar idea for the the other direction of the proof. Now, other properties of this scheme. So we have the following. The connection with the distance of the code. So if you consider this construction, if you take, so the first statement here is every subset of at least n minus t plus 2 participants is an authorized set. And then every subset of at most, this is the dual distance. So d perp minus 2 participants is a forbidden set. It appears that it has a property of the ramp scheme. You remember the ramp scheme that I discussed earlier. So it has the property of ramp scheme. But take note, these quantities, n minus d plus 2 and d perp minus 2, they are not tight. So you can have better bounds for the authorized sets and the forbidden sets. Now, next I will discuss the connection with MDS codes and threshold schemes. So basically they are equivalent using this construction. So first we recall MDS codes. So MDS codes, they satisfy the singleton bound. You can just look at the linear code case. So if you have an NKD linear code over FQ, they satisfy this inequality. So K is at most n minus d plus 1. And if you have equality, so you have what we call the maximum distance separable codes. An example of MDS code is the Reed-Solomon code that I gave earlier. It's an MDS code. Now, some of the properties of MDS code. So the following statements are equivalent. So C is an NKD code over FQ, and then G and H are, G is a generator matrix, H is a parity check matrix for C. So the following statements are equivalent. C is MDS. Every set of K columns of G is linearly independent. And then the dual code is also MDS. And then every set of n minus k columns of H is linearly independent. So some of the characterizing properties of MDS code. So now let's look at the connection between threshold schemes and MDS code. So this is one direction. If you have an m plus 1 k MDS code over FQ, then there is a secret sharing scheme based on C that is an ideal linear Kn, K out of n threshold scheme. So if you have an MDS, it implies threshold scheme. So this is the proof. Going back to the construction, you can see it is linear and ideal. So again, ideal, the size of the share is the same as the size of the secret. Okay, so if you remember, the shares and the secrets are field elements in this construction. So it is an ideal scheme. Now, since C is an MDS code, so we have the following distance and dual distance. So distance is n minus k plus 2. Dual distance is k plus 1. And then we apply the one of the theorem before. That theorem is this one. So every subset of at least n minus 2 participants is authorized. And then every subset of at most d perp minus 2 is forbidden. So if we apply this using the values of the distance and dual distance, so what you get is the following. So every subset of at least k participants can recover the secret, and then every subset of at most k minus 1 participants have no information about the secret, so it's a k out of n threshold scheme. And then this is the other direction. If you have an ideal linear threshold scheme over FQ, so there exists an M plus 1K MDS code over FQ. So the proof is longer. So I leave it as an exercise for you, the proof of this one. So what happens here is, since they are essentially equivalent, so if you obtain results from on MDS codes, so it translates to results for threshold schemes. Or if you obtain results on threshold scheme, you can apply it to the problem on MDS codes. Okay, so let us define the following code words with certain properties. So we call it minimal code words. So first we define the support of a vector. So the support of a vector V is the set of positions, non-zero positions of the vector. So set of all I such that V sub I is non-zero. So if you recall the Hamming weight of a vector, it's the cardinality of the support of the vector. And then we say that a vector V covers a vector U if we have this property. So the support of U is contained in the support of V. So an example is the following. So you can see that the vector V covers the vector U because the support of U is a subset of the support of V. So what do we mean by minimal code words? So essentially it means code words with minimal support. So minimal with respect to set inclusion. So a non-zero code word is minimal if it covers only its scalar multiples and no other non-zero code words. So another way of saying it is it has minimal support. Now, minimal code words were introduced by Huang in connection with decoding. And then it was reintroduced by Massey in connection with this construction of secret sharing. So examples for minimal code words, let's consider this binary linear code, C, with this generator matrix. So we can list down the code words. And then the minimal code words are this three. So you can check that the supports are, these are the minimal supports. So there is no other non-zero code word that is a proper subset of the supports of these code words. So now what's the connection with secret sharing of these minimal code words? So Massey proved the following. It is related to the minimum access structure. So let's recall again the minimum access structure. So these are the authorized sets that are minimal. So if you have a subset that is a proper subset of a minimal set, so it's not authorized, it's not in the set. So essentially this theorem says that if you have a minimal authorized set, it corresponds to a minimal code word of the dual code. So if C is an n plus 1 linear code over FU, if you construct the secret sharing scheme based on C, so if you have a minimal authorized set, it corresponds to a minimal code word of the dual with this property. So the first coordinate is 1, and the support is this, which corresponds to the participants of the subset. So that's the connection between the minimum access structure and the set of minimal code words of the dual. So I will show again one direction of the theorem. So suppose A is a minimal authorized set, And suppose these are the shares. So since it is authorized, they can recover the secret. So the secret is a linear combination of the shares. Now, from this linear combination, so the non-zero constants, you can use this to form this vector. So this one comes from this. So if you form this vector, you can check that it will be in the dual code. Here you have the, what this means is the dot product is 0 of this code word and the code word used in the secret sharing. So the dot product is 0. So that's why it follows that this will be in the dual of C. And then if you look at the support, this is the support of this code word, and it should be minimal. It should be a minimal code word. Because if it is not a minimal code word, so what will happen is, if it is not a minimal code word, you will have a non-zero code word with this property. And then what will happen is it will contradict the minimality of this authorized set. So it should be a minimal code word. Now, one question that you can ask concerning this construction is, so if you recall, the secret is just one field element of the one field element. So is it possible to extend the construction? It's possible. So you can make the secrets bigger. So an extension is the following. Suppose the set of possible secrets is this one. So FQ to the L, where L is at least 2. And then let us assume that the possible shares are FQ. So one field element. Of course, you can generalize it to any size. But to simplify, we just assume this for the shares. So suppose this is the secret. So length L vector. So to apply the construction, this time we use linear code with length L plus N, and then dimension K and minimum distance D, where the minimum distance is greater than the length of the secret. And then you consider this generator matrix, so essentially the same construction. So you compute this code word such that the first L coordinates are the secrets. And then you give the other coordinates as the shares of the participant. So that's the idea. Now, since the size of the secret is, or the size of the share is smaller than the size of the secret, this one is non-perfect. It's a non-perfect scheme. It doesn't provide perfect security.